Hello everyone and welcome back to episode 6 of the video series on computational models. In the previous episode we concluded by stating a theorem about the recurring or terminating nature of rational numbers. In other words, a characterization for whether a given fraction will be terminating or recurring by inspecting only the interplay between the denominator and the radix of the number. At the very end of this episode, we will prove this theorem, but first, let's gain some familiarity for this characterization by discussing some examples in different bases, specifically base 10 and base 2. We will also look at some other elementary theorems that we will need to prove the main result. So as a first example, consider the fraction 1/3 which expands as the decimal number 0.3 recurring. To write the recurring number as a fraction, we look for the order of the expanded notation, which is to say that we multiply it by the length of the cycle of the recurring digits and finally subtract the two results, thus eliminating the recurring digits, and finally solve x, giving us a rational expression. Conversely, starting with the fraction 1/3, we can perform long division to obtain the recurring expression 0.3 as follows. Note that throughout the long division process we encounter a never-ending procedure. It is recursively subtracting 9 from 10 and bringing down the next 0 digit, resulting in this tail of 3's. Here's another example in which we investigate the decimal expansion of 1/7, which is 0.142857 recurring. Similar to before, we look for the length of the recurring cycle of digits, which in this case is 6. So multiplying by 10 to the power of 6, or the base to the power of 6, and subtracting and reducing the fraction, we get that this is equivalent to 1/7. Conversely, starting with 1/7, we perform once again long division, and after having done this routine 6 times, we see a recurring decimal of 142,857 recurring, having length 6. Now let's turn our attention to base or radix 2 binary fractions and investigate the similarities and differences for the above technique applied to 1/3 and 1/7 in base 2 representation, in other words as a sequence of bits. The technique is similar in base 2. We shift the binary point by the length of the cycle before eliminating the recurring tail. The only difference is that this is done by multiplication of the base 2 to the order of the length of the cycle of the digits, in this example shifting the binary point by 2 units right. We perform a left bit shift by 2 units. Note that the bit shift operation in hardware versus the dot or float point shift operation on paper is what confuses most people. This is because left bit shift corresponds to moving the float point right, while right bit shift corresponds to moving the float point left. Now we proceed as before by eliminating the recurring cycle, thus obtaining the finite expressions for the numerator and denominator. This has the side effect that the left hand side is in binary base 2, while the right hand side is in decimal base 10. This is due to the fact that we have essentially expanded the expressions upon multiplication by a power of base 2 on the left hand side, and on the right hand side we have subtracted the previous bit string from it to eliminate the recurring bits of digits, but simultaneously we treated the left hand side as decimal base 10 when subtracting 1 from 2 to the power of 2, which is 4 in base 10. The type of a number on the left hand side versus on the right hand side, subject to the relation of equality, or rather strong equality, must be equal in all aspects, including the type of the number. Left bit shift means the bits, more specifically the bit addresses, need to be incremented on a physical addresser as a result of having performed bit shift using exponent notation on the page versus having performed bit shift in computer memory. The left hand side must now be converted back to binary base 2 notation. It remains for us to convert the coefficients of x to its binary or bit representation, which is in this case 1, 1, and finally write the binary fraction as 1/1, 1. Conversely, for converting the fraction 1/1, 1 to its dot or point notation equivalent, we perform long division as before. It's worth noting that computer hardware has no intuitive notion of fractions. In other words, the number 1/1, 1 is not stored as such. The number 1 over 1 1 in computer hardware is stored as 0.0101010101, using as many bits as necessary or required to closely approximate the true value of 1 over 1 1, thus causing a loss of precision when working with fractions. Thus, for programmers, it's important to be aware of the internals of computer hardware when working with fractions, specifically to correctly handle loss of precision. Because loss of precision is a real concern that sometimes needs to be considered or taken into account when designing softwares that intricately manipulate small or minute quantities in a system, in very much the same way that we have to be careful when working with very large quantities to prevent type overflow and interpretation errors, which is why some programming languages like Python has built-in capabilities for working with large quantities. To combat the loss of precision, computer engineers devise impressive techniques for modeling fractions like the IEEE 754 standard and other symbolic algebra systems like the Wolfram language and SymPy. Let's head over to Jupyter Lab to demonstrate the concerning matter in the context of Python, Java, C#, and C++. So in Python, comparing the raw values of 0.3 to that of 0.1 multiplied by 3 returns false. This is because of the loss of precision when converting the value 0.3 to its binary representation when stored in computer memory. We try a couple of strategies to see what's happening under the hood. By inspecting the decimal equivalent value converted from the float point number stored in memory, we see that for 0.1 multiplied by 3 gives us an overflow, while conversion of the float point for 0.3 results in an underflow. Thus, 0.1 multiplied by 3 is slightly bigger than 3, while 0.3 itself is slightly less than 3 in computer memory. In Java, the effect is similar, where comparison between expressions that are the same in normal mathematics, it is done on paper, actually returns false. Due to the internal arithmetic of adding or multiplying fractions, we get an overflow for the float point double 0.1 times 3. In contrast, 0.3 as a numeric double is actually equals to 0.3. Once again, determined by some underlying internal procedures, which can be observed by printing out the decimal equivalent of the binary bit string stored in memory. The behavior of handling floats and doubles in C# is similar to that of Java. Using formatted printing, we can see the decimal equivalent values of 0.3 and 0.1 multiplied by 3 as stored in computer memory, which demonstrates that these raw values are not actually equal from the most significant bit. Similar to the other languages, the same effect can be observed in C++, for which 0.3 in binary double format corresponds to an underflow, while 0.1 multiplied by 3 corresponds to a binary double format overflow. The floats have a precision of about 7 significant digits, while doubles have a precision of about 15 significant digits. Often programmers build simple comparator functions to check for near equality using an epsilon threshold. Here's a final example that demonstrates the binary format equivalent of 0.0010010001 recurring for the fraction 1 over 7. Similar to before, we look for the order of the binary point expansion. It is the length of the recurring cycle of digits, which is 3 in this case, then multiply the expression by 2 to the power of 3, which is 8 in base 10, and finally eliminate the recurring digits. Again, we convert the left-hand side back to decimal base 10 and write the result as a binary fraction. Now for the converse, to compute the equivalent binary bit string for the rational 1 over 111 in base 2, we perform long division once more. Now that we have seen some examples of the first theorem, let's try to prove it. It is, we are required to prove that any recurring or terminating number in any base or radix b expressed in dot or point notation can be written as a fraction. The proof of this is very similar to the numeric computations as discussed above. To prove this, consider any number x which may be recurring or terminating. Then, according to our discussion of the previous episode 5, we can express x as lambda dot mu over line chi, where lambda is the whole or the integer part, mu is the finite part of length n, and chi over line is the recurring part of length m. Now there are two cases to consider. If m is 0, then the expression is finite, and we can convert the expression to an equivalent fraction by multiplying the dot or point notation representation by the base raised to the power of n, where n is the length of the finite part. Now, if m is not 0, or if m is greater than 0, then the expression is recurring, and we can convert the expression to an equivalent fraction in 2 steps. First, we identify the length of the recurring cycle, which in this case is m. Then we apply the geometric series formula for the nth partial sum to calculate the sum of recurring cycle of digits in the expression, and then add it back to the finite part, which has already been written as a fraction. Note that the geometric series expression for the chi terms starts at index 1. It is the constant ratio r is associated with the radix or base b to the power of negative m starting at index 1, and the leading term a, which is the chi terms up to m terms, constitutes the m digits of the recurring cycle. The key observation is that a does not appear as the first term in the decimal expansion of the geometric series. Thus, to maintain equality, we subtract a from the infinite sum. By simplifying the expressions, it's easy to see that the result is a fraction, since all denominators and numerators are finite integers or whole numbers. Hence, we obtain a fraction or a rational expression. Thus, we have just proved that any terminating or recurring number is rational in any base b. Now we are ready to provide a high-level overview of the main theorem, which states that if a fraction x having numerator n and denominator d, such that n and d have no common factors other than 1, is a fraction in any base b, then the denominator d has a prime factor or prime factors that are not prime factors of b if and only if x, the fraction itself, has a recurring dot or point notation representation. This theorem gives us a formula to determine whether a fraction will be a terminating or a recurring expression. Here's some examples in base 10 to better demonstrate what the theorem statement is about. By looking at all of the following fractions, some of these are recurring in dot point expanded notation while others are not. The question is, how can we tell before performing any algorithm to compute the expansion of the fraction whether it will be recurring or terminating? The theorem tells us exactly how to check for these properties. The theorem is essentially a decision algorithm and dictates that we must inspect the interplay between the denominator of the fraction and the base or the radix of the number system to decide. Specifically, we have to compare their prime factors. It is, we have to do the following. List out the prime factors of the denominator d, then list out the prime factors of the base or the radix b, then check if all prime factors in d are also prime factors in b. If so, then the fractions will be terminating, otherwise the fraction will be recurring. Let's see if this checks out. By computing the dot point notation for the above fractions, we get that a half is terminal because 2 appears in the prime factors of the base 10. A third is recurring because 3 does not appear in the prime factors of the base 10. 1 over 4 is terminal because 4 can be factorized as 2 times 2, both appearing in the prime factors of 10. 1 over 5 is terminal because 5 appears in the prime factors of base 10, and so forth. Now we can do the exact same thing in base 2. For example, the binary fraction 1 over 1, 0 is equivalent to 1 over 2 in base 10, which is terminal in base 2 because 2 appears in the prime factors of the base 2. 1 over 1, 1, which is equivalent to 1/3 in base 10, is recurring in base 2 because 3 does not appear in the prime factors of the base 2. 1 over 1, 0, 0, which is equivalent to 1 over 4 in base 10, is terminal because 4 is 2 squares, thus having only prime factors from the base 2. 1 over 1, 0, 1, which is equivalent to 1 over 5 in base 10, is recurring in base 2 because 5 does not appear in the prime factors of base 2. 1 over 1, 1, 0, which is equivalent to 1 over 6, is recurring because 6 can be factored as 2 times 3, but 3 does not appear as a prime factor of the base 2, and so forth. Note that in the theorem statement, the condition that the greatest common divisor of the numerator and the denominator must be 1 is necessary, since if not, then we could encounter situations in which we are not immediately able to decide or apply the theorem. For example, 1 over 6 is recurring in base 10, but 3 over 6 is not. This is because the numerator and the denominator of 3 over 6 has a greatest common divisor of 3. Thus, upon reducing the fraction, only then we may apply the theorem to see that the resulting fraction, 1 over 2, is actually terminating. Okay, so to prove the main theorem, we first need to prove the following number-theoretic facts. First, the infinitude of primes. It is Euclid's proof that there are infinitely many. This is needed because when working with large integers, there must be some guarantee that, quote-unquote, we can always find a next larger prime when factoring integers into its unique prime factorization list. This brings us to the second most important theorem for our journey to prove the main result. Second, the fundamental theorem of arithmetic. It is the unique prime factorization theorem. It's the statement about integers that any integer can be uniquely expressed as the product of prime factors. Indeed, we will need an understanding of Euclid's division algorithm number 3, the statement about the division algorithm that guarantees the existence and the uniqueness of a quotient q and a remainder r when dividing two integers, say a and b. Finally, Euclid's lemma, the statement about primes that if a prime divides a product of any two integers, say a and b, then the prime must divide one or the other or both. And if that prime does not divide one, then it has to divide the other. To prove the infinitude of primes, we follow the standard argument form that reasons by way of contradiction. So, suppose that the statement is not true, then it should be that there are only finitely many primes. Thus, we can actually enumerate all primes. So suppose that there are n number of primes, say p1, p2, p3 up to pn. From this list of primes, we can construct a new number which we will prove to be prime by taking the product of all those in the original list plus 1. So it's easy to see that this newly constructed number is prime because none of the already known primes from the list can divide it, since there will always be a remainder of 1. This shows that the constructed number is actually prime, but not included in the original list, thus contradicting that we can actually enumerate them all. Hence, it is true that there are infinitely many. Since we've arrived at a contradiction via the assumption that there are finitely many, that leads to an absurdity. We can conclude that the opposite of that assumption should be true. In other words, there are infinitely many. To prove the uniqueness and existence of quotient and remainder for the Euclidean division algorithm, note that we usually treat the division algorithm without regards for the sign of the numbers involved. In other words, we restrict our attention to positive integers, since it's simple enough to adapt the algorithm to work for negative numbers as well. Note that dividing any integers a by another integer b is equivalent to finding numbers q and r, quotient and remainder, such that a can be written as the product of the quotient with b plus the remainder r. We now prove the existence of a quotient q and the remainder r. To do this, consider the set S consisting of the numbers a minus bk, where k is any integer, such that the expression a minus bk is still always positive. In other words, we are subtracting multiples of b from the numerator a. Okay, and so S contains those numbers that remain by subtracting b from a k times. In other words, the largest k, such that the difference is still positive, is the quotient, and its difference with a is the remainder r. Note that the set S cannot be empty since a is itself contained in it. Thus, at the very least, there exists a quotient q, which is 0, and a remainder r, which is a itself, when dividing a by b, specifically if a is less than b. Now the set S contains all possible remainders when dividing a by b, but we are interested in finding the smallest remainder and the largest quotient. This can be achieved by finding the largest integer value k such that a minus bk is always still positive, but a minus b times k plus 1, the next larger integer, results in a negative difference. The value k for which this condition holds will be the quotient q equals k, and the difference a minus b times q will be the remainder. Now it remains to prove that r less than b is the minimal such element of the set S, and q equals k is the largest such element that results in the smallest remainder difference r. In other words, r is the smallest element such that the difference r equals a minus bk is greater or equals to 0. To prove that r is minimal, suppose, by way of contradiction, that it is not, then r is greater or equals to b. So in other words, r minus b is positive but less than r, and we can continue to divide b into a at least once more, say q plus 1 times. And indeed, if r is greater or equals to b, then we can write a as the product of q plus 1 and b plus the remainder r minus b. Reducing this expression still gives us bq plus r. So r minus b cannot be the minimal such remainder element of the set S. Now we need to establish the uniqueness of the quotient q and the remainder r. To do this, we again argue by contradiction, by supposing that q and r are not unique, in which case there is at least one other quotient q prime and another remainder r prime, such that we can express the numerator a in two different ways. Since both expressions are equal to a, by transitivity of equality, the expressions on the right are also equal. So by eliminating a and factoring out b and rewriting the equation slightly, we get that r prime minus r is equal to b times q minus q prime, which shows that b is a divisor of r prime minus r. In other words, r prime minus r is a multiple of b, but since both r and r prime are less than b, so is their difference. Thus, it must necessarily be the case that r prime minus r is 0, since a divisor of a number which is greater than the number itself must be 0, thus proving the uniqueness of the remainder r equals r prime. Now substituting r prime minus r equals 0 back into the previous equation, we get that b times q minus q prime is 0. But b is not 0, so by the zero product law, it must be that q minus q prime is 0, thus proving the uniqueness of the quotient q equals q prime. Next, we prove Euclid's lemma that states that for prime p, if p divides a product of integers ab, then p has to divide a or p has to divide b. Again, reasoning by contradiction, suppose that p divides the product ab, but p does not divide a and p does not divide b an integer number of times. Then for both a and b, by the Euclidean division algorithm, there exists quotient q1 and q2 and non-zero remainders r1 and r2, such that a can be expressed as pq1 plus r1 and b can be expressed as pq2 plus r2. Now, by taking the product of a and b and using the fact that p divides the product, we have that there exists some integer k such that pk equals ab. And then equating the two expressions for ab, we have that pk equals the product of pq1 plus r1 and pq2 plus r2. However, since r1 and r2 are both less than p, we cannot factor p on the right hand side, which contradicts that ab can be expressed as a multiple of p. Thus, the assumption that p does not divide either one of a or b leads to an absurdity. Hence, it must be that p divides one or the other. To prove the fundamental theorem of arithmetic, we have to show that all numbers can be expressed as a unique product of smaller prime integers. So suppose for some integer number n that it is not the case that it has a unique prime factorization. Then there exists at least one other factorization of the number n. We will show that all prime factorizations of the number n must be the same. In other words, they are in fact unique. Note that by Euclid's lemma, all the primes for a prime factorization are coprime. It is the greatest common divisor of any two primes in the same list is 1. However, in the two distinct prime factorizations of the number n, it may be that two primes in two different factorizations are not coprime, but since they are prime, they must be equal. But since a prime divides n, it must divide one of the primes in both lists. Thus, any prime in the first factorization must divide only one of the primes in the second factorization, in which case the two primes in the two different lists must be equal. Without loss of generality, we can assume that both lists are in ascending order. Then the smallest prime in the first list divides the smallest prime in the second and are equal. Similarly, the second smallest prime in the first list divides the second smallest prime in the second list and are also equal. By continuing this process all the way to the last prime in the two lists, it's easy to see that the two lists have the same number of primes and the prime factors are all equal. Thus, the prime factorization of a number is unique. At long last, we are ready to prove the main result for this episode, which is the characterization theorem that allows us to decide, whenever expanding a fraction, whether it will be recurring or terminating, and vice versa. Suppose the denominator of the fraction n over d has prime factors that are not prime factors of the base or the radix b. We must show that x n over d has a recurring dot point notation representation. Now suppose by way of contradiction that x does not have a recurring dot point notation representation, then x must have a terminating or a finite point dot notation representation. So x, being the fraction n over d, can be written in the alternate form a over b to the power of k for some integer exponent k. By rearranging the expression for x, we have that n times b to the power of k equals a times d. Now let p be such a prime factor of d, which is not a prime factor of b. Then p divides ad on the right hand side, since p divides d. Thus p must also divide the left hand side, n times b to the power of k, since the left hand side is equal to the right hand side. Now by Euclid's lemma, since p is prime and p divides n times b to the power of k, it must be the case that either p divides n or p divides b to the power of k. However, the greatest common divisor of n and p is 1, since we are given that the fraction n over d is in reduced form. Thus p does not divide n, therefore it must be the case that p divides b to the power of k. Now since p divides b to the power of k, and b to the power of k is just k factors of b written as b times b times b k times, it must be the case that p divides b. So p is a prime factor of the base b. But this contradicts the assumption that d does not have prime factors that appear in b. Thus, our assumption that x has a finite or terminating point dot notation representation leads to an absurdity. Therefore, it must be the case that the fraction x equals n over d does not have a finite terminating point dot notation representation. Hence, x must have a recurring point dot notation representation as desired. Here's an alternate proof of the same fact using a contrapositive argument. So suppose that x has a finite or a terminating dot point notation representation. We will prove that the denominator d and the base b must have the same prime factors in common. Since x has a terminating point notation representation, we can express the fraction x equals n over d as a series up to a finite index n as follows, involving the base b and the finite part of the mantissa mu in increasing negative powers of b up to n. Now multiplying throughout by b to the power of m makes the exponent of b positive throughout the series, resulting in an integer on the right hand side. Therefore, the left hand side, which appears to be irrational, can also be reduced to an integer. Thus, the denominator d divides the numerator n times b to the power of m, but the greatest common divisor of n and d is 1 by assumption, so it must be the case that d divides b to the power of n. Hence d divides b, giving us that the prime factors of the denominator d are also prime factors of the base or the radix b. Now, to prove the converse of the main theorem statement, we will argue by contraposition once again. So suppose that all prime factors of the denominator d are also prime factors of the base or the radix b. We have to prove that the fraction x, which is n over d, has a finite terminating dot point notation representation. By demonstrating that the fraction can be expressed as some integer a over b to the power of k for some integer exponent k, and an appropriate numerator a. This is quite simple, since multiplying the original fraction n over d by b over b, we can rewrite and manipulate the original fraction as having a numerator n times b over d and denominator b. Then, since b and d have common factors, we can reduce the numerator to eliminate d, reducing the numerator to an integer, and we are left with denominator b having exponent k equals 1. Thus, we have successfully written the fraction x equals n over d as having a finite terminating point dot notation representation in base b. Here are some concluding remarks to eliminate any confusion that you may have and avoid misinterpreting the statement of the main theorem. So, the property that, quote unquote, a number is irrational is independent of the base b in which we choose to express the number. This is often a source of confusion. The property that a number is irrational in a given base is not something that we can prove. Rather, irrationality of a number is a property inherent to the number itself, not the base. In other words, if we prove that a number is irrational in, say, base 10, then it is also irrational in any other base. This is similar to saying that a number is prime or a number is even or odd. It is a property that is inherent to the number itself, regardless of the base in which it is written. So this brings us to the end of episode 6 on the theory of computational models. In episode 7, we will look more into the IEEE 75/4 standard and how fractions are actually stored in the hardware of a computational device, as well as some other interesting properties of numbers that we wish to capture when encoding numbers into hardware.